Thank you, Elena. So, well, thank you, everybody, for coming, despite the weather. I know it's nice outside. So, as Elena said, I'm working now in Japan. I'm an assistant professor at Hokkaido University, which is located in the northernmost island of Japan. So it's been living in snow and 0 degrees to come here, which is nice. So I just wanted to thank Elena for the opportunity to be here, and I start with the presentation now. So what I'm going to talk about to you today is kind of an overview of climate change and how climate change is changing biodiversity patterns from the level of species populations up to ecosystems functioning and servicing, and how that is influencing us. So the first, I just wanted to give a very general overview of how the thermal environment from this macroecological perspective is. And here, so you can see that this is a graph from the IPCC report where you have the last, since the 1970s, and you can see the energy, the heat from anthropogenic warming that has been absorbed by the different components. So you have there the ocean is in blue, dark blue, deep ocean, upper ocean in light blue. And it's astonishing that the ocean has absorbed 93% of this heat produced by anthropogenic warming. So when we hear about ice melting and increases in temperatures in the atmosphere and so on, it's just 7% of this warming that has been accumulated from global climate change. Which means that thanks to the oceans, the impacts of climate change on the atmosphere and on land has been much less dramatic than what they are already. One of the reasons for this, so when we think about that, we may think that the impacts on the ocean are much larger because it's absorbing all this excess of warming. But in reality, if you see at the increase of temperature that has been going on since the 1950s, so the blue line is the ocean, global ocean, and the red line is the land, the atmosphere, you can see that for the global ocean, it has increased about 0.5 degrees on average. Whether from in the atmosphere on land, it has been about 3 times that amount, 1.5 degrees. And one of the reasons for this is, among other things, is that the water has a very high specific heat content. So it takes about 3 times more energy to increase 1 degree, 1 gram of water than what it takes to increase 1 degree, 1 gram of soil. And that means that the ocean is warming at a lower rate. Again, when we hear this, we may think that, okay, if the ocean is warming at a lower rate than the land and the atmosphere, maybe the impacts of climate change on the ocean are not so strong. Maybe we don't need to care so much about the ocean. However, the fact of this specific heat content being so high, it also means that in cold places and in warm places, the variability in temperature over time is much lower in the ocean than on land. So the ocean warms up slower and cools down at a slower rate than on land. So when you see this is the temporal variability over land and over the ocean, you can see that the land in latitude, 5 degrees latitudinal bands, you can see that variability is much stronger on land than what we have in the ocean. And what that means is that small changes of temperature in the ocean for species that are adapted to this stable environment are more dramatic than for species that are adapted to a more variable, fluctuating in terms of temporal dimension environment. This is also something that happens at the spatial scale. So if we look here, what we have is a map of the spatial gradient in temperature at the 1 degree resolution. So it's comparing in these 1 degree cells, each cell with a 3x3 neighborhood. So it gives you the change in temperature as you move across the space, in this case in kilometers. And those red colors are a strong spatial gradient, so you change the temperature rapidly as you move across the space. And as you can see, they are much more dominant on land than for the surface of the ocean. These are the temporal trends over the last 50 years or so in temperature of the surface, so for the surface of the ocean and the surface of the atmosphere. And you can see what we were saying, that the trend in temperature is much stronger on land than in the ocean. When you divide those two things, so temporal trends by the spatial gradient, you get something called climate velocity, which is an index that basically tells you how fast those lines, the isotherms, that temperature has moved across the space over time. So basically, it's in kilometers per decade in this case, so it's telling you how fast you will have to move to remain in the same temperature you are today in the future. And what you can see is that on a global pattern, the velocity is actually roughly the same on a global average for land and for the ocean, but for different reasons. In case of the ocean, it's because we have these very shallow thermal gradients. So when you divide, the velocity increase, meaning that in the ocean, the species have to move farther to keep the thermal environment. And that also means that having a thermal environment, especially that is more variable, makes available for terrestrial species a more variety of thermal environments of these microclimates that they can exploit as well to find climate refugia, which are not so readily available on the ocean. So that's kind of at the larger scale the thermal environment. So it's a thermal environment that is not changing in terms of temperature very rapidly, but is moving fast. So how does that affect the species at the species level? Well, we normally, it affects at the level of the physiology of the species. And what we normally refer to is this kind of physiological thermal tolerance curves, where you have on the x-axis the temperature of the body of the species, and on the y-axis you have some measurements of performance. It can be growth rate, it can be reproduction rate, things like that. And what you normally see is this kind of skewed, left-skewed bell-shaped distribution, where you have a peak where the performance is maximum at some optimum temperature, and as you move away from that maximum, then performance decline. There are a few things to note here. One is that these thermal tolerance curves are not only variable depending on the species, so you have some species that are generalist, so they are adapted to a wide range of thermal environments, so the breadth of the thermal tolerance is wider, but that comes at a cost at a lower performance maximum. And you have some species that are specialized to some thermal environments where they do very well there, they achieve high performance at the optimum temperature, but the range of temperatures where they are found are narrow. And this variety of thermal curves is not only at the species level, but it's also within the species level. So populations, depending on where they have the environment that they have been adapting to, those curves can change. Life stages within the same species also can change, so it's very variable. So that's one of the things. The other thing, that you can see is that because this is not symmetric, changes in performance that comes from warming to go to the warming side of the curve are much faster than changes in performance that comes from cooling. So the same amount of warming or cooling produce higher decrease in performance on the warming side. And the reason, because of that, many species, the peak of abundance is not at the optimum temperature, but you found it somewhere on the cooling side of the curve to allow for some buffering against environmental variation. But when you put that into the biogeographical range of a species on a simplified way, this is kind of the process that you see. So you have climate change that is modifying the environment where that species live, and depending on how so those points are local populations within the range of the species, and depending where that population is within the physiological tolerance of the species, the warming can create positive effects or negative effects. So if it is on the cooling side and is warming, the performance will increase, and you would expect the species to do better under warming. If it is on the warming side and it's going down the slope, the performance will decline, and you will expect the species to do worse than what it's doing now. When you are in a range where you have the different local populations, there will be some places at the warm trailing edge of the species where temperatures are becoming too hot, and those local populations will become extirpated, so you have a range contraction. At the cool leading edge of the species range, you have environments that are currently too cold for the species to be there, but under warming they will become climatically available, and providing the species can disperse and settle and reproduce, you will have that range expansion. And when you combine both things, you have the dynamics of the range under climate change. Of course, this is a simplification because, as you well know, warming is not the only thing that dictates where species can be found. There are other climatic variables and also species interactions and other things. But from the point of view of climate warming, this is kind of the process. One thing that is important also is that for marine exotherms, they seem to fulfill the thermal environment more completely than terrestrial ectotherms. So I don't know if you can see this plot well, but it's from a paper of Jennifer Sunday, where she was looking at how different terrestrial and marine exotherms, the current distribution, fulfill the thermal breadth of the species. And you have, so if there are many species there, 140 or something like that, which are the points. So if those, this is the median for all the species measured, if it falls on the 0 line, that would be that those species, the places where you found them today, are fulfilling, are occupying the full breadth of the thermal tolerance for those species. If they are below, that's underfilling, and means that the species are not found in all the localities where they would be able to be found, providing they fulfill the full thermal envelope. If they are above, that means that the species are located in places that are colder or warmer than you would expect based on the thermal envelope. And what you can see is while terrestrial exotherms go above and below, for the marine exotherms, both at the warm boundary and cold boundary, the median is pretty much on the 0 line. So that means that marine exotherms seems to be fulfilling more the thermal envelope, and the meaning of that in terms of distribution shifts on the climate warming would be that you would expect them to be more vulnerable to change, to respond more readily to change in sea temperatures. So what are the expectations then under climate warming for these biogeographical distributions? So the expectations first is for the species to go to cold places. So you would expect the ranges to go either north or south, depending whether you are in the northern or southern hemisphere. And this is something that on a general pattern at the global scales, we are actually observing. So this comes from a meta-analysis, the most comprehensive meta-analysis that have been done so far on marine changes in marine distributions under climate change from Polachanska in 2013. That's kind of the global map where the blue sectors and the blue points correspond to responses of the species that are in agreement with climate expectations. This global map is not only distribution shifts. Here are also things like phenological shifts. But the point here is that you can see that there is a good agreement of observed responses with expectations from climate change that is kind of in different regions of the world. And when you check about how different taxonomic groups are responding, which are all those that you have there, you also see that in general terms, everything is also going according to expectations, so it's shifting towards higher latitudes, which are the points above that 0 line. Of course, this is a general trend. When you zoom in and you start looking at more regional patterns, you start to see variability. This is a study from Pinsky in 2013 in Nature, when he was looking at bottom troll surveys across the continuous United States for commercial species. And what he found was, as you can see, depending on the sectors where you are and depending on the regional patterns of warming, the species there seems to be much more variability in the response. So some places you have this shift towards the north, other places is shifting towards the south. Here in the Gulf of Mexico, they are shifting towards the west, and so on. And those black arrows are the mean response for the whole assemblage in that part. But again, you cannot see that. But if you zoom in here, you will see that these arrows that are the individual taxa, they are doing very different things from one another. Sometimes, so the point here is that it's very important. We have these global trends, but it's very important to try to understand that variability, because often what is challenging is not the trend, the norm, but that variability is what is challenging adaptation and doing management. In that particular thing there in the Gulf of Mexico, what was happening is not that the species, there was no response, but that the species were deepening in the distribution. So they were going deeper. So this is another of the expectations that we have, is that when you have warming, and if the species can go deep, normally they find cooler waters in deeper places, so they will go to deeper parts of the ocean. And this is something that is also been observed in different places. This is from a study that we conducted in the Northern Sea, where we were looking at distribution shifts of benthic invertebrates. And you have there, this is the past, and this is the current condition, so 15 years gap between those two time points. And you can see that a lot of these species have been shifting their centroid of the distribution towards deeper waters. So they are below this one line there. And sometimes the shift is really dramatic for just 15 years. Sometimes we have shifts of 6 or 8 meters down of the centroid. Another thing that we have been looking at to try to understand this variability that is not explained simply by changes in warming patterns is ocean currents. So we have been looking, using this metadata set of Polachanska that I was presenting before, we were looking at how about if we created an index that is capturing the agreement in direction between warming and the flow of the currents, how that extra predictor could improve these climate expectation models. So there you have the map of this index, where if you have red colors is that warming and the ocean currents are going in the same direction. If you have green colors is that they are going in opposite directions. And you can see that there is noise, of course, but in general terms, where you have poleward warm currents, poleward flowing warm currents like the Kuroshio current in Japan or the Brazil current and so on, you have predominantly red colors. And where you have ocean currents that flows towards the equator and bring cold waters towards the equator, like the California currents or the Humboldt current, you have the predominantly green colors of that index, right? So when we use this index, we actually improve dramatically the predictive power of the models. So we went from about 40% to about 66% of prediction power. But what we were also interested was to try to understand what was this effect that was improving the models. So what we did was to take the residuals from the climate expectation model. As you know, the residuals are observations minus predictions. So if you have positive residuals, there would be responses that are going ahead of the climate signal. If you have negative residuals, there would be responses that are lagging behind the climate signal. And we divided by where the shift was reported, whether it was at the leading cold edge of the distribution or whether it was at the trailing warm edge of the distribution. And what we find that is when this directional agreement between warming and ocean currents increases, then range expansions at the cold edge also increase. They are going faster. It's something that you would expect, right? If warming is going that direction and the ocean current as well, the species will be able to disperse and keep track of the thermal envelope faster. On the trailing edge, however, we found the opposite effect. So we found that when this mean directional agreement was positive, the contraction rate, especially for benthic species like invertebrates or algae, the contraction rate was faster. Slower. So the explanation of the hypothesis that we were giving there as explanation was that maybe when you have this situation of the ocean currents going in one direction and the warming in the other, what you have is some kind of damping effect where populations at the central part of the distribution of the species are seeding individuals because of the ocean currents towards the trailing edge population, and that can create maybe those central populations are adapted to colder waters, and there can be some kind of dampening effect of maladaptive effect on the trailing edge population, so they contract their range faster. But it's something hypothetical. We didn't have data to test that. In any case, as I was saying, there has been a lot of work going on trying to explain this unexplained variation because of warming. And there have been some studies that have been looking at the method of detection. So what is the influence of the way you measure the distribution of the species, and you calculate these centroids and range edges. And that study found that 22% of the variation in response comes from variation in the methodology. Here is what I was saying about the ocean currents, that we passed from 40 to 66% of explained variation. And also some studies have been looking at life history traits, how those can help explaining how a species respond to climate change. And that goes up also to 57% of explained variation. And then there are other many important factors that still we don't know very well because there have not been many studies in that direction, but things like species interaction or habitat availability, quality, abundance of habitat, and of course other climatic and non-climatic stressors as well are important. So there is a lot of work that still needs to be done there. Okay, so we pass now from species population level to community level. So when you have all these species that are responding to warming and changing the distribution, maybe what you would expect is that if you have a community at a local place and it's getting warming, some of the species that are adapted to more colder water will retreat, and you will have new species arriving that are adapted to warmer waters. No? And this is more or less what we are observing, again, at these macroecological large-scale patterns. So this is a study that we have now in review in Nature Climate Change, where we have taken bottom troll surveys from different parts of the Atlantic and the Pacific coast of the United States, and also plankton from the continuous plankton recording. And here, in this part of the paper, what we are trying to see is how changes in temperature are followed by changes in community composition from the point of view of the thermal traits of the species that comprise those communities. So we use something that is called the Community Thermal Index. I don't know if you are familiar with. It's something that was proposed initially for terrestrial species, so it has been used a lot with things like butterflies and birds. And what is basically is you have your community that is composed by different species, and each of those species has one of these thermal breadths to which they are adapted to. So if you take the median temperature for the thermal breadth of each of the species, and then you calculate the median of those medians for the community, you have this community thermal index. And basically what it is, the community thermal index, is an indication of the proportion of warm affinity and cold affinity species in the community. So if the community is gaining warming affinity species, you will expect the community thermal index to increase because it's the median for the community. And if it is gaining cold affinity species, it will decrease. So what you have there is for the last, since 1985 to 2014, these are the warming trends, the sea surface temperature trends This is 1 degree. This is just put in boxes of 5 degrees by 5 degrees. And these are the fish communities and the plankton communities. And as you can see, there is some variability, but in general terms, where it has been warming up, the community index has increased, meaning that they have been, the relative proportion of warm affinity species have been increasing in those communities. So it follows the expectations that you will have. Another thing that we have been observing, and this is also observed data, comes from a study looking at coastal fish communities in the northwest coast of the United Kingdom. And what they saw, what was also over time, what they had was a very strong process of biotic homogenization, meaning that the species from different parts of this coast, they were increasingly similar in community composition over time. So this is the distance decay in dissimilarity in the past and in present times. And as you can see, in the past, the communities were much more different as you move away than what they are now. And this is also a process that is being partly driven by climate change, because normally what you have is that contractions of the range are slower than expansions of the range. So at least in an initial phase, what you have is that those communities that are separated in space, they are increasingly sharing a higher number of species. And this is something that we also are predicting that is going to happen in the future, intensify in the future. So this is a work that we did to model global marine biodiversity patterns and the future climate change. So this is the current species richness situation with the well-known pattern of high species at the tropics. And these are the two situations for under the RCP 4.5, so a moderate warming scenario, and the RCP 8.5 business as usual scenario. And what you have of what we projected that will happen is that you have this strong loss of biodiversity in the tropics and a net increase in biodiversity in temperate and high latitude waters. That doesn't mean that there is no extinctions there, but it means that the number of species that are arriving in those places is higher than the number of species that those places are losing. And what was interesting to see was that these latitudinal patterns that we found, they resemble very much what has happened in the past. So this is for coral species, also latitudinal, at different latitudes, the species richness at present and during the last interglacial period, so 125,000 years ago. And you need to rotate this to be in the same axis, but you can see that this pattern of a large decrease in tropical areas is basically what we are predicting that will happen under the most extreme scenario by the end of the century. We also look at changes in community composition, both in time and in space. So there again, you have the moderate warming scenario and the business as usual scenario. And this is the temporal change in community composition. So same localities over time, how they are going to change in the composition of a species. And red colors are large changes in composition, which are, again, concentrated in the tropics and also in Arctic and Antarctic regions. For different reasons. In the tropics, it's because of this strong loss of a species, and in the polar regions, it's because gain of a species. On a spatial scale, so here what you have is at the same point in time comparing different localities. Those orange colors are communities that will become increasingly similar, so sharing a larger number of species. And again, you can see that especially the temperate regions are places where there is this biotic homogenization process is going to be, or is projected to be, especially strong. Coming back to the present again, what we are interested in is in these biogeographical transition zones, right? Because they are kind of the front line of these changes. These biogeographical transition zones are regions where you have, so where you go, for example, from tropical to temperate waters, or from boreal to Arctic waters. And in those regions, you have many species that are the range edge, either the warming or the cold range edge. So what happens there is when you have warming, then these range edges will shift, and you have rapid changes in community composition as well. So those places are places like, for example, the Bering Sea or the Barents Sea. Japan is a place where we have a lot of changes, the east coast of Australia as well. And this process is being called tropicalization, it's being called borealization, Atlantification, depending on where you are. But basically, is this process of communities losing cold adapted species and increasing in warm adapted species. One of these hotspots of this tropicalization process is Japan, and it's where I've been doing some work. And Japan is a very good place to study these processes for many reasons that are listed there. So it's, warming in Japan has been kind of double the global average over the last 100 years. It has a very wide latitudinal range, 25 degrees, the Japanese archipelago. So we go from tropical or subtropical waters to subarctic waters in the north, in Hokkaido, where I live. It has an almost continuous chain of islands, which is about 7,000 islands of different sizes that are scattered along this latitudinal gradient. And that creates a stepping stone kind of sequence that the species can use to change the distribution following warming. It's also important that we have this Kuroshio-Tsushima current system that flows from the south to the north and encircles the Japanese archipelagos on both sides and brings warm water towards temperate latitudes. So that intensifies the warming process, but also helps dispersion of the species. And then also, of course, a very important thing that is necessary when you do analysis is that we have data. So the Japanese have an amazing database that they have been collecting for the last 70, 80 years of corals and macroalgae distribution along the coast of Japan. Okay, so the tropicalization process that is going on in Japan is basically a process where you have temperate kelp communities, like those, that under warming, they have been receiving tropical fish and tropical corals that are expanding the range from southern latitudes. And if this tropicalization process continues, what you normally ends up is with the coral reef that is developing and the macroalgae contract the range and disappear. Sometimes that process don't follow that path, and what you have is that the kelps just become depleted because of grazing from the herbivores, but there is no substitution by corals, and you end up with this kind of barren landscape, which is called by the Japanese isoyake, which is a really low productive, low diversity seascape. So what we did here, we used this fantastic database and we extracted some species. I think it's around 30, 40, 45 species of kelps and fucoids, macroalgae, some herbivorous fishes, and corals. And these are ordered from from colder places or temperate waters to tropical waters, right? Those are more warm affinity species. And the first thing we did was to observe distribution shifts over the last 40, 60 years for those species. So there what you have is expansions of the leading edge for the species, contractions of the trailing edge for the species. And you can see that for the expansions, we mostly have corals and especially herbivorous fish that has been expanding the range of the southern part of Japan very quickly. So the fish, on average, the median is 18 kilometers per year. Corals, the median is 4 kilometers per year, but some species of corals have been shifting up to 10, 11 kilometers per year, so really fast. And at the same place, on those same localities, we have kelps and temperate kelps and temperate fucoids that are contracting their range from the same places. What was interesting also to see is that corals are expanding their range into existing kelp communities, but also into kelp communities that have been deforested by fish in equal proportions. That was a surprise, because normally the process that we expect is that fish, because they expand their range faster, they will arrive first, and then they overgraze the kelp communities, open a space for the corals to arrive, and the corals then displace the kelps. But sometimes it doesn't happen, and they are actually in interaction, in competitive interaction in those communities. The next step was to develop some models to try to reconstruct those observed shifts using, again, climate velocity and ocean currents. And there in the top panels, what you have is the relative importance of ocean currents in explaining those distribution shifts. And it's basically what we found before. So for leading edge expansions, currents are much more important than for contractions of the trailing edge. And those are the predictions from, so you have the predicted response and the observed response, and that's the one line. So in general, what we found is that all the species are lagging climate. So they are shifting, but they are not shifting fast enough to keep pace with the changes in climate. We use the models also for predicting the future. So these are predictions for 2035. And what you have there is the probability of this community shift from temperate kelps to coral reefs in Japan in the future. So you can see that the expansion of this tropicalization process now is concentrated there, but in the future is expected to expand to most of the central south part of Japan. The challenge now is to understand what are going to be the consequences of these shifts in community, right? Because especially for Japanese people, macroalgal beds are very important, but of course corals are also very important. And this range expansion of the corals in some way is an opportunity for the corals, because in their home range they are under a lot of pressure from warming and other human-related pressures. And both corals and macroalgae are very, give a lot of ecosystem services to the community. So of course, both of them maintain very high biodiversity. Corals offer coastal protection. Algae, you have carbon sinks and an oxygen pump, and you have tourism and so on. So it's very difficult to establish what would be the outcome of these changes in the community, right? And we think that adaptation of the local communities and local businesses is going to be a key factor. So how they are going to be able to adapt to these changes in communities that are bringing these changes in ecosystem services. And this is an example, a good example. So this is a fish market in Okinawa, in the southernmost part of Japan. And those two species there, that one and that one, which is a drummer and a grouper, they are some of the fish species that are expanding the range into central Japan. And we were talking with a local fisherman there, and he was saying that these fishes are not consumed in central Japan, but they are appreciated in South Japan, and they are starting to fish them and send them over to the southern islands, because they are starting to see the business. So if these are emerging fisheries, if these fisheries establish and grow, in the future it might be the case that they are profitable for the local fishermen in central Japan, and you have a new resource developing. So it's just an example of how climate change is not only created impacts, but it can also create new opportunities. And this brings to the last part of the presentation, which is about these high-level ecosystem services impacts. And it's about fisheries. And I think many of you are much more expert than me on fisheries science, and you know probably all these numbers. But it's just to make the point of how important fisheries at the global scale are, right? So they provide, wild fisheries provide about 80 million tons of seafood per year, which represents 20% of the animal protein intake for over 40% of the population, and maintains either directly or indirectly 1 in 10 people at the global scale, right? So there is a lot of interest in trying to understand how climate change is going to influence global fisheries. And those studies make headlines because the importance of this global resource, right? These global studies, however, they are mostly dealing with the effect of climate change on fisheries, but they don't take really into account the effect of management on top of the effect of climate change. So they consider kind of a static management environment. There have been also attempts to study the same problem from the other point of view, like this paper from Christopher Costello and Steve Gaines, where they were looking at how the global stocks status will develop into the future if you change the way you manage those stocks. So you can see this is the current situation, and these are the future trajectories, depending on whether you employ a business as usual management scenario or more scenarios that try to maximize the benefit of the fisheries at a long temporal scale. The trajectory that those stocks follow is very different. But the problem here is the opposite. They are considering a static environment, so they don't take into account the effect of climate change. So what we wanted to do in this study was to try to bring both things and see how climate change can modify the status of global fisheries, but using also management to try to see how management can modify that effect of climate change on the fisheries, right? So what we did, we took the global fisheries database from this Costello paper that I just saw, and we modeled the effect of climate change on the distribution of the fisheries stocks using the climate velocity model also that I showed you before. And then we implemented the effect of these changes in distribution into the bioeconomical model that Costello used to understand the effect of management on the fishery status. And what we did, we changed the management scenario to see if the effects of climate change on those fisheries were different depending on how you manage the fishery. We considered two effects of climate change on the fishery stocks. One was changes in productivity, where we look at how the biomass of the fishery changed over time because of climate change at the given locality. And that, of course, affects future yields. And that is important from the management point of view, because if you keep managing a fisheries as you do, but the fisheries is changing, you may end up in a situation where you are under-exploiting or over-exploiting the resource. What we found in the projections, so each of these lines is one fishery stock, and the x-axis is time. On the y-axis, you have there the change in biomass. And these are the different RCP scenarios, so from the most mild scenario to the high business as usual scenario. And as you can see, is that depending on the amount of warming, the trends, you have a lot of change in the trends. So this is the median for all the stocks, and you can see that under the most moderate scenario, there is not much change on average. But you can see that under the most extreme scenario, you have around 30% of change at the global scale on average for all the stocks. Another effect of climate change on fisheries that is very important and is becoming more awareness of this effect is the changes in the distribution, the spatial distribution of the species. So there was this paper, maybe you have seen it this year, showing the number of transboundary shifts of these stocks across countries. And that creates, of course, tensions because the resource is moving, but the places where people can fish the stock are not moving, so they are fixed in space. So this is the other challenge that we were looking at, changes in the distribution of the species, which affects where you can fish the fish and who have access to that fish, right? And what we found, it was also this strong effect of warming on the number of transboundary shifts that you have. So again, we go from the most moderate climate scenario to the business as usual scenario. And this is the percentage of these 900 stocks that are shifting from at least one country. And as you can see, under the most extreme scenario, the percentage is much higher, but also we have this green bar is pointing to stocks that are both leaving countries and entering into new countries. So the next thing that we did was to look at management scenarios. So we consider 4 scenarios where we went from no adaptation to full adaptation. So basically, the no adaptation means you don't adapt to either the productivity change or the change in distribution of the species. The full adaptation means that you adapt to both challenges. And the way you adapt to both challenges for the change in productivity, what you do is that you use this economically optimal management where you fix your fishing rate depending on the biomass that you have. So you look at how the biomass is changing over time, and you adapt your fishing mortality rate to the available biomass. In terms of the distribution change, if there is no adaptation, what we consider was that the management declined towards a situation of steady state open access, which means that there is a race for fishery, that people just maximize the benefit, short-term benefit, so they try to fish as much as possible before the resource leaves the country. And what we found that, again, the 4 RCPs scenarios there, and you have the 3 measures: profit, harvest, and biomass. And the green bar there is the full adaptive management strategy. And as you can see, for all but the most extreme scenario, we found that the fully adaptive management strategy provided higher profit, harvest, and biomass at the global scale for these fishery stocks. Another thing that was important as well was that these are all the individual stocks. And there you have a relative change at the end of the century relative to today. And this is changes in harvest and changes in biomass. And you have that, okay, the stocks that are going to do better under the fully adaptive management strategy are not so many. So it's 20% of the 900 stocks that we were looking at. But the important thing is that those 20% account for half of the total yield, global yield of the fisheries. And that means that targeted management approaches where you try to do this fully adaptive management strategy on some very large stocks can have a large impact at the global scale. So we found that at this global scale, a better future is possible, but you need to address both challenges, the productivity and the distribution challenge. You need also to challenge not only the management, but also the climate change is very important. We saw, depending on the path that climate is following, business as usual scenario create much larger impacts than more moderate scenarios. And a very interesting thing is that we need this kind of cooperation among nations. We have been doing a recent analysis of international agreements between different countries on fisheries, and we found that out of 127 agreements that we have reviewed, none of them mentions climate change. So climate change is not on the table at all, even though the expected impacts because of these transboundary shifts are high. So just to finish very quickly, the future work, which is the work I'm discussing with Elena and we want to move towards, is kind of understanding how these changes in species, in populations, in community, in ecosystems are going to influence people and businesses at the local scale, so ecological adaptation at the regional scale. In Japan, we are working with this tropicalization process. We are very interested to see how different systems of management and protection, marine protection areas, will influence the outcome of this tropicalization process. I think I'm running out of time. In the Arctic, we are also interested in looking at how this distribution shift of Arctic species that are used by indigenous people will also challenge the sustainability of those Arctic indigenous communities. Okay, so just finish with some slides. Again, to bring the message that climate change, of course, is having a lot of negative impacts in the marine environment. But together with those negative effects, there are also some positive effects emerging, right? And they are not many, but they are important. And I think that's also part of adaptation, is recognizing not only the negative impact, but also the opportunities that are there. So you try to maximize those opportunities to try to keep the balance as much as you can. So I leave you with this quotation there to think about, and thank you all for listening. Thank you.